Yeah, good afternoon once again to all the students. Welcome to the week two NPTEL program for the Electrical Machines 2 course. So last week we discussed some basic concepts on the magnetic circuits, and we discussed what exactly inductance is, how do we calculate inductance of a coil, and what is self-inductance, what does a mutual inductance mean, and some concepts on coupled circuits as well. And we started some concepts on dot convention. We solved some numericals based on that. Now, before going into this week's topic, last week some students asked uh, to discuss some more time, to spend some more time on the dot convention, because there was a bit of confusion among the students in the last week. So I thought of discussing a bit more about dot convention this week, starting with that concept, and we will discuss some basic conventions and few more insight into the dot convention this week, and then we will move to some other concepts which were taught during this week. So yeah, let's start about a simple concept on the dot convention. Last week we saw a specific application of dot convention because dot convention was already there and we discussed it. But now we will see from basic what exactly is a dot, what exactly does a dot convention mean, and how it helps the total circuit in aiding, in opposing, and based on the dot convention how we can determine the polarity of the circuit that we will see today. So we will start with that and then we will move towards the week two concepts. And yeah, I hope my screen is visible and I am audible. And with that, let's start today's discussion. Let's start today's discussion with dot convention. Moreover, this dot convention will be in coupled circuits. Coupled circuits dot convention. Excuse me for the handwriting, it's a bit distorted when I'm using this tab. Okay. Anyway, can anyone tell me when do you call a circuit to be a coupled circuit? So, what is your understanding of a coupled circuit? Anyone? So, when do we call a circuit to be a coupled circuit? Okay. So, let me explain what exactly a coupled circuit means. Second. Yeah. So, an electric circuit. Yeah. Screen not available. Is screen not visible? Uh, Hello, Kumar or Pawan, is screen visible to you?
Yes, sir.
Okay,
Sir,
okay. Shubir Saha, maybe you check your internet connection or something because I have shared the screen. It's
yes, sir,
visible.
I'm visible.
Okay. Yeah, it seems Shubir Saha cannot see our screen. Shubir, once check your internet connection because I have shared the screen and yeah, Kumar and Pawan confirmed it. Yeah, maybe rejoin. Yeah. So yeah, let's move. Let's discuss. So an electric circuit is said to be coupled when there exists any mutual inductance between any two coils. Let's say we took an electric circuit, and there exists a mutual inductance between the coils present in that particular electric circuit. Then we will say that the two coils are coupled, or we can say that that particular electric circuit is coupled. So yeah, that is the basic definition. Let me write and said to be a coupled circuit if there exists a mutual inductance between the coils present in that particular circuit. So yeah, whenever there exists mutual interest in a circuit, and we can easily say that, or we can easily determine that that particular circuit is coupled. Now we will see the dot convention. Yeah, before seeing the dot convention, we will see what are the different kinds of dot convention that are available. So that's important, right? Now, let's see the definition of a dot convention technique. So we call it a dot convention. So it is a technique which gives details about the voltage polarity at the dotted terminal. Let's say we have a circuit and we have placed some dots in circuit. So whenever you see a magnetic circuit, you will see randomly placed dots at the coil's starting point or ending. So it says that that particular dot will give you details about the voltage polarity at that dotted terminal. So why it is useful? So why the polarity is useful? Because whenever you are solving for a KVL or you are solving some kind of circuit analysis, this dot terminal is useful for you so that you can determine the polarity, voltage polarity at that point. So that's the use of that's the use of your dot convention. Now we will see what exactly it represents. So there are two cases. Now if current enters at dotted terminal, just trying to now, yeah, if a current enters the dotted terminal of one, let's say, of one coil. Now now there is a coil and we have placed a dot at that coil, and the current may enter or the current may leave from the dot. Now based on the current polarity, we should be able to say what is the polarity of the induced voltage. Now yeah, now we are saying that now my current is entering at the dot terminal. So if the current is entering at the dot terminal of one coil, then it induces the voltage at another coil. So that's how this mutual coupling works, right? So it will induce a voltage at another coil which is having a positive polarity at dotted terminal. It induces, we can say voltage. It induces voltage at another coil. This is important. Another coil which is having positive polarity at dotted terminal. Now we will clearly look at it. What exactly does it mean, and we will solve. We will draw some circuits, and we will look into what exactly this dot and positive polarity means. And the second obvious case will be if current leaves a dotted terminal of one coil, it it induces voltage at another coil. Now it will be having a negative polarity, which is having negative polarity at the dotted terminal. Now, so sorry, yeah. Now, these two are the only cases which you will see in a couple circuit which is having a dot. Either the current enters the dot, or either the current leaves the dot. So now we will see how what kind of couplings we'll have in this dot convention, and we'll also see some basic circuits and how this dot convention will help in understanding the aiding connection and how it will help in understanding the opposing connection. Now, yeah, basically this uh, coupling circuits, coupled circuits, we will see first how many types of coupling is possible. Classification of coupling. Now, if you look at different types of coupling, you will see two main types of coupling. That is electrical coupling, and second one, can anybody? It is, yeah, it is magnetic coupling. Now, but yesterday we have seen both types of coupling in circuits. That's why that was the first time maybe you are looking at electric coupling and magnetic coupling. That's why I understand you must have faced difficulty. That's why we are discussing in very basic case from now, because today we will see what exactly electrical coupling mean and what exactly is a magnetic coupling mean. Maybe then you will have you will not be having any problem understanding it. Yeah, first one, electric coupling. Yeah. So when does this electric coupling happens means yesterday we saw this kind of coupling in the problem we solved. Yesterday we solved a problem where the coils are connected in series. It means that there is a wire, physical connection existing between these two coils, if you remember. So that kind of connection is called electrical coupling. So I will give you a definition so you can remember it. Electrical coupling occurs when there exists a physical connection between two coils. That is very important. Physical connection should be there. So this coupling can be of either aiding type or opposing type. That we will look into later. But the basic of an electric coupling is there should be a presence of physical connection. Now, when it will be aiding, when it will be opposing, that it depends on whether the current enters the dotted terminal or leaves the dotted terminal. When we look into some diagrams and when we look into some voltage equations, you will clearly understand what is aiding and what is opposing. Now, I hope you understand what is electric coupling. Electrical coupling means electrical coupling occurs when there exists a physical connection between two coils. So that's important. Physical connection should be there. Now, let's step into electrical coupling of aiding type. Aiding. What is the meaning of aiding? Aiding means to enhance, to help, uh, to go along with it. Opposing means in the opposite. So we are opposing something and we are aiding something. Now first we will look into the aiding kind of electrical coupling. Within electric coupling, I'm just writing it. Physical connection. It should be there. Now within electric coupling, we are looking at aiding type. What is electric coupling and what is aiding type? So we will see it. Now, since this electric coupling have a connection, let's say we take two coils and we will connect them in series. Yeah. Okay. Now I'm taking two coils. This is coil number one, and this is coil number two. Now, yeah. Now I've connected them in series. Once I connect them in series, I have given a voltage, input voltage of V. Let's say this is L1 and let's say this is L2. Both are connected in series. Now, when I try to pass a current I through this circuit, since the both are connected in series, same current will flow through both the coils. That's the property of a series connected coils. Now, I am placing dots. So, pay attention carefully. Now, I have placed a dot here and I have placed a dot here as well. Now, when two coils are connected in series and I have given some kind of circuit, this is how a circuit will look like. And when there are two coils, we know that there exists a mutual inductance part. So L1 and L2 are the self-inductances of the coil, and between these two coils and between these two dots there exists a mutual inductance, that is M. Now the dots are at the initial point of the coils L1 and L2, and M is the mutual, V is the input voltage, and I is the current. So everything is clear now. Now, in this case, you can see that the current is entering at the dotted terminals of each inductor. Now, this is the direction of the current, right? This is the direction of current. Now, at this instant, the current is entering the dotted terminal. For the coil 2 also, the current is entering at the, this is the direction of current. The current is entering at the dotted terminal. Now, what we have, see, what we have written earlier, read the first point. So if current enters at the dotted terminal of one coil, it will induce the voltage at another coil which is having positive polarity at the dotted terminal. So that's how it mutually induces the voltage. Now, since it is having a dot terminal here, I'm looking at here, and at this place, the current is entering. So then it will induce a voltage in the coil number 2. In this coil, it will induce a voltage where positive polarity will be at the dot. Here, the second coil is having the dot at here. So I will write a plus here, and the negative will be here, and it will induce a voltage here. Now we know the magnitude of the voltage here as well. What is it? M d I by dt. So this I is due to the current flowing through the coil number 1. So since it's a series connected, the current will be same. So M di by dt. What important is this polarity, plus and minus? Why this is plus? Because the current is entering in this coil. So the voltage induced in the secondary coil will have a positive polarity at the dotted terminal because that's the current is entering. Now, okay. Now we have understood the polarity of the voltage in the second coil. Now come to the current entering in the second coil. Now if we see, I am looking at this point. Current is entering here as well. Here as well, at the dot, the current is entering. Again, we will read the first point here. Now, if the current enters at the dotted terminal of one coil, it induces voltage at the another coil, which is having positive polarity at the dotted terminal. So, this is why exactly I have written these two statements. So, you don't get confused. Whenever you see a dot, you go to that statement and read it. If the current enters a dotted terminal, it will induce a voltage at the secondary coil. That is obvious. Voltage will anyhow be induced. But what is the polarity? It should be same polarity, positive polarity at the dot. Now, see the second coil. At this point, the current is entering the dotted terminal of the second coil, and this will induce a voltage in the coil 1, where this dot position will have the positive here and negative here, and the magnitude is M, that is mutual inductance, which we take here, di by dt. So this I is the current flowing through the coil 2. Since it's a series connected coil, both currents will be same. Now this is what circuit will look like. But why this dot placements I have drawn in aiding type? Why this kind of dot placement is called a aiding type? So that we will look now. Why it is called aiding type? Now we have marked all the connections and everything was okay. Now let's apply KVL here. KVL means Kirchhoff's voltage law. Now if you write simple KVL equations, so this is the loop, and I will write it. V is equals to, let's write the inductance polarities will always be same based on the current flowing at plus minus plus minus. Let's first write the self inductance values. L1 di by dt plus L2 di by dt. Now these voltages plus M di by dt plus M di by dt plus M di by dt plus M di by dt. Now I'm taking common di by dt. That's the common, right? L1 plus L2 plus 2m. M and m are same, and di by dt is common. Now it's looking like the equivalent inductance, because now if you look at from this side, this is L equivalent. We can replace it with. So L equivalent value is equals to L1 plus L2. These are self-inductances, and 2n. This is twice the mutual inductance. Now you see here, L1 and L2 are the self-inductances that we know. This M mutual inductance is actually aiding the circuit. Now this is helping the circuit in increasing the inductance of the entire circuit. Equivalent inductance is increasing because of this mutual inductance. Excuse me. So yeah, that's why it is called the aiding type. Aiding means enhancing, improving, or increasing. Now the same kind we will see for a opposing type. It's simple, same concept, but just with the difference in the placement of dot polarity, the inductance will change. We will look into that. Now opposing type. Please keep in mind this opposing type and aiding type we are discussing in the electrical coupling, because there is a physical connection between these two coils. They are connected in series. Now again, I will take same coil connected in series. I will give a voltage and I will pass a current here, and this is L1 and this is L2. But what I will do now is I simply change the placement of one dot. For coil 1, the dot I will remain at the same place, but coil 2 I will place the dot here. Now the mutual inductance will be existing here. See, I have changed the dot position of the coil number 2. Now see, can anyone explain me the polarities of the mutual inductances in this coil? It's very simple. You find where the current is entering, and we will mark the polarities of the mutual inductances. So yeah, let me explain this. The current is entering here. Take the first coil, coil number 1. In this coil number 1, at the dot polarity, current is entering. So when a current enters a coil, it will induce a voltage in this coil where the polarity is positive at the dotted terminal. Now here the dot is here, so the positive polarity is here. This will be the negative. Now the magnitude is di by dt. Fine. Now look at the second coil. It's different in this case because the current is entering here and the current is leaving the dot here. If a current leaves the dot, let's go back to that statement. So read the point number B here. Now this point. If a current leaves at the dotted terminal of one coil, it induces the voltage at another coil which is having negative polarity at the dotted terminal. Now current is leaving at the coil 2 and it will induce a voltage at coil 1 where the negative polarity will be at the dotted side. So here the minus will be here, negative polarity. The plus will be here. The magnitude is same, M di by dt. Now, if you try to write the KVL as we did for the aiding case, now V is equals to, let's first write the self-inductances, L1 di by dt, L2 di by dt, minus M di by dt, minus M di by dt. V is equals to taking di by dt common, minus 2m di by dt. So this is again equivalent in inductance if you look from here. Now L equivalent, what we got? L1 plus L2 minus 2m in case of series connected in a opposing kind of connection. Just because of the dot placement, now our equivalent impedance is decreasing. My mutual inductance is making my entire impedance reduce. Previously, twice the mutual inductance. 2M is aiding, but in this case, twice the mutual inductance is opposing the self inductances. So that's what we are trying to look at, how the dot placement will give the polarity. So the dot terminal will always give you the voltage polarity at the dotted terminal. So that's very simple point. And let's now look at the magnetic coupling. This is how exactly happens in a transformers where there is no any physical connection. I will just okay. Okay. Let's look at the second kind. We have seen electric coupling. Now we will see magnetic coupling. So this is actually important for our case because usually in all kind of transformers and coils, we see there is no electrical connection, there is no physical connection. So this is what magnetic coupling exactly means. So if we want to look at the definition, so it occurs when there is no physical connection between two coils. So again, this can also be of aiding type, this can also be opposing type, but aiding or opposing will just depend on the place where we are placing the dots. So that the dot terminal will determine the aiding kind or opposing kind of magnetic coupling. Now within this magnetic coupling, let's look at aiding type quickly and then we will go for opposing type. Aiding type. Now let's first draw how a magnetic coupled circuit will look like. There should not be any electrical connection, right? Physical connection should not be there. And let's consider a general transformer circuit where we will see, excuse me, where we will see a magnetic coupling but not any electrical connection or physical connection. Now, yeah, this is L1, this is L2, primary side, secondary side, and I'm giving a supply of V1 in the primary side, and that will make a current of I1 flow in the circuit. I will give a supply of V2 in the secondary, so that will be responsible for the flow of current I2 in the secondary. 1 second. Yeah, I2 in the secondary, and I am placing the dots now. Let's say dot placement is important. So I have placed dots at these two positions. Now my mutual inductance will exist between these 2 points. Now everything is there. This is the magnetic coupled circuit. There is no physical connection, and if this is the connection, now the currents will flow through primary coil and secondary coil. Those are I1 and I2 respectively. Now in this case, if you see the currents entering or leaving at the dotted terminal, can anyone tell? If you see the circuit, the currents are entering at the dotted terminals of respective coils. If you see this one, the I1 is entering and I2 is also entering the dotted terminal. Now, if you remember that point, if a current enters the dotted terminal, so in this case, the induced voltage in each coil will be having the positive polarity at the dotted terminal because of the current passing in the opposite. So this first we will look at the induced voltage due to this I1. Due to this I1, induced voltage will be present at the secondary coil. Voltage will be induced at the secondary coil where the positive polarity will be at the dotted. So here this is the plus and mutual inductance is M, but the current is due to the I1 I1 by dt and di1 by dt. That's important. Now let's look at the induced voltage because of current I2. So I2 is also entering this coil at the dot. So it will induce a voltage in L1 where the magnitude will be M di2 by dt. The polarity will be plus at the dot here, minus at the dot here. Simple. Now this is the aiding type of connection. Why it is aiding type? We will see. We will see now. And same thing. Let's write the KVL for primary side. Primary side. What is the equation? V1 is equals to. I am writing the self inductance first. L1 di1 by dt plus, this is the plus here, let's try plus m di2 by dt. Now we can't take di common here because the currents responsible for these both inductances are different. The self inductance here is in both equations. If you see, self inductance and mutual inductance have same polarity, but it is because of the different currents in it. Now if you see, if you write the KVL for secondary side, V2 is equals to L2 di2 by dt plus m di1 by dt. So why this is called an aiding type? Because in both this equation, self-inductance is L1 and mutual inductance is M is having the same polarity. That is an example of a magnetic coupling circuit of aiding type. Now let's look at another type. That's the second type, which is opposing type of magnetic coupling. Now same circuit, let's take a transformer with primary and secondary. So core, secondary, and I have given voltage V1 here, and I have given voltage V2 here. V1 is responsible for I1, V2 is responsible for I2, and this is L1, and this is L2. Yeah, now see, I am placing a dot in the coil 1 here, and I will place a dot in the coil 2 here. I have changed the dots. Now there exists mutual inductance at here and here. Now let's see. Here the same circuit, but in this case dots are changed. In the primary side, if you see, the current is entering the dot. If the current enters the dot, it will induce a voltage in the secondary coil where the positive polarity will be at the dotted terminal. Here the dot is, here the plus will be coming, and here the minus will be there, and the inductance will be mutual. The current responsible for is I1 mdi1 by dt. In the secondary is the where it will change. Now if we see, the current is leaving the dot in secondary. If the current is leaving, it will induce a voltage in the other coil, which is primary here, where the polarity at the dot terminal will be negative, and the other polarity will be positive, and magnitude is mutual inductance M. The current responsible for it is di2 divided by dt. Simple. Just because of the dot placement, we will get the opposite polarity of the mutual inductance. Again, we will quickly write the KVL equations for primary. V1 is equals to inductance. Self-inductance remains the same. LdI by dt. The magnitude is remains same for the mutual, but the polarity, if you see, it's minus here. Minus m di2 by dt. And secondary, if you see, V2 is equals to L2 di2 by dt minus m di1 by dt. So important thing to remember or pay attention is the currents are different in these both equations, because mutual is always caused by the uh, current passing through the other coil. It's not due to the same current. Now here as well, self and mutual, if you see in this opposing type, the self inductance and the mutual inductance are having different polarities, positive and negative. That's why it is called a opposing kind of connection, opposing kind of dot polarity. So yeah, that's what I wanted to discuss on the dot polarities. I want to discuss in deep because there should not be any confusion. So I hope now we are having even more better understanding on the dot concepts, like how what kind of circuit is called a coupled circuit, and within coupled circuit, what exactly does a dot convention mean, and within dot convention, what is explains. So this current is entering at the dotted terminal. What explains it? What is the polarity? Everything is. I hope it is clear now. Now, yeah, we have seen what are the different types of coupling altogether: electrical and one second. Yeah, electrical and magnetic coupling. And within this electrical coupling, we have seen two types: aiding type and opposing type. Electrical coupling, we will say electrical coupling when a circuit is having a physical connection. So, if the magnetic coupling is a circuit where there is no physical connection, within the magnetic coupling as well, we have seen two types, that is aiding type and opposing type. So, yeah, with that, we will close the discussion on the basics of magnetic circuits there, of the dot convention, inductance, self inductances, and now we will start our discussion for this week, where we will be looking at some basic motor and generator aspects. Not exactly in the rotating machines, that is AC machines, but we will see some basic concepts. So we will discuss two main rules that are very often used in this electrical engineering. So that are very important before going into the actual concepts of machines, of rotating machines. So this is what also discussed in this week's for your course. We will also look into a bit more now. So let's try to understand better these two rules, which are very often used in electrical engineering. Now let's start. Now, starting with, let's say we have a conductor of finite length. Let's say the length of the conductor is L, and it is moving with a velocity v. I will just try to draw it here. Excuse me. Now, this is the conductor of L, conductor of length L, and it is moving with the velocity v in this side. So, yeah, in this way, in this part, this is moving. Now, let there be magnetic field. So let's say we are placing that particular conductor, which is moving with a velocity v, and let there be a magnetic field present all along this plane. So now the conductor is placed here. In this diagram, the conductor is placed here, and this is the entire plane. So let there be a magnetic field present along the plane of the paper. Now whose strength is B. Now B is the magnetic field intensity, which we denote by the letter V, and this represents the magnetic field across the plane of the paper. But the direction of the magnetic field will be into the paper. So into the paper means we use the convention cross, right? Cross means into. So if you want to imagine this particular figure which we wrote, let's say here there is a pole, and here there is a pole, north pole and south pole. In between I have placed the here it is I have placed the conductor like this. This is the conductor of length L, and I have placed it here, and I am moving, I am moving the conductor in this direction. So L, length L, with a velocity v, I'm moving this direction. On top of it there is north pole and south pole. So we know magnetic lines of force will go from north pole to south pole, so like this. Now that's what we are trying to draw here, into the pole. So across all this plane, we will have magnetic field on top. Cross means into the paper. You can see if this presentation is a board, we are going into the presentation. Now let the xy is the conductor. Let's say these are the terminals of the conductor xy of length L. Then what happens is, between these two terminals xy and between these two terminals xy, an EMF will be generated. So that's the law. What is the magnitude of EMF that is generated? BL. Yeah, exactly, Raju. So this magnitude of EMF is BLV, where B is the magnetic field intensity. That's the units will be. I just quickly write the equations. B equation B units will be Weber per meter square, or usually represented as a Tesla. The length is in meters, and the velocity will be in meters per second. So we are trying to keep everything in the SI units. That's why we are taking everything in meters per second. So while solving problems, you have to make sure if they are in what units they are asking. Are they asking in meters per second or centimeters per second? Length is given in centimeters or meters. That's where you have to pay attention. Now, yeah, this one we all know. EMF is equals to BLB. But what should be the polarity of this? What should be the polarity? Is this plus minus or minus plus? So that's important. So how to find the polarity? Anyone? Plus minus, yeah. Why it is plus minus and which law it is used to find the polarity of the voltage induced? Anyone? It's the basic law. Okay, right hand rule, correct. So what exactly? So for the other students, Raju has correctly said that we use Fleming's right hand rule to determine the polarity of the induced voltage. Now we will see what exactly Fleming's right hand rule is and how we can determine the polarity using the Fleming's right hand rule. Now I'm just writing Fleming's right hand rule. RHL means right hand rule. Now, everyone take your right hand, and we know this is the forefinger, and this is the middle finger, and this is the thumb. Okay. Now, your forefinger. What does the forefinger denotes? Anyone? Forefinger denotes the direction of magnetic field B. Okay, and middle finger. Anyone? What does middle finger denotes? Middle finger. One second. Yeah. So middle finger. Let's try to add middle finger data because that's what we are looking at. First, type thumb. Yeah, thumb. We can say thumb denotes direction of velocity, and then with your middle finger help, precisely, if I want to say tip of the middle finger. Tip of the middle finger will give you the positive polarity of voltage. Okay, is it working now, Raju? Hello, uh, hello. Yeah, hello. Am I audible now? Hello. Am I
Yes,
audible?
sir.
Okay, okay, okay. Thank you, thank you. Okay, okay. Let's continue. Sorry for that. Yeah. Okay. Yeah. So our now, yeah, we can see our tip of the middle finger will give the positive polarity of the voltage induced. So that's how we will find the polarity of the voltage. Now you are looking at the figure here. At the top right, we have drawn the figure. Now, what is the value of what is the direction of the magnetic field here? That is into the paper, right? Now, everyone take your right hand and your forefinger. That will denote the direction of your magnetic field. That is towards into the paper. So, like this, this is towards the floor. It will be into the paper, and now or you can take like this as well if it is into the paper, and this is the velocity, and this is the velocity, and this is thumb. Now the tip of the middle finger, now this is the tip of the middle finger. Now tip of the middle finger will give the positive polarity. Now here is the positive and here is the negative. Now this is our middle finger, and yeah, this is our thumb, and this is our forefinger. So this is B, this is V, and this one, this is tip of the middle finger. This will give the induced EMF polarity. So this is positive and this is negative. Now if you try to with respect to xy, if you see, uh, this is x and this is y, and if you see, there is a positive here, there is negative here. So it's like if you place a battery here. Now this is positive and this is negative. Yeah. Now, if at all our magnetic field is constant, and if at all our velocity is constant, so the induced voltage will be also DC. Constant DC voltage will be induced. So that's how we will find the polarity of the induced voltage using Fleming's right hand rule. Now, if we reverse the polarity, I mean, how can we reverse the polarity of this plus and minus? Simple. We have to reverse the polarity of the magnetic field. Okay, now let's say our magnetic field is dot in place of cross. Now, if it is, sorry, now if it is dot here, that means it is coming out. Now again, take right hand. Now this is forefinger. It is coming towards me, and thumb will be this one, and yeah, it is thumb will be this one. And see, my tip of the middle finger will be downside. So this will be positive. That means you will have x, and this will be positive, and top will be negative. This kind of will be with respect to xy. With respect to xy is important. So yeah, you just have to reverse the magnetic field to get a reverse polarity. It's important. So yeah. So finally, what exactly this rule says? Uh, let's say we have a conductor moving at a constant velocity v, will be having an induced voltage E, provided that particular conductor is placed in a magnetic field of strength B, and the direction of B and V is mutually perpendicular. So that's very important. So here if you see, V is in this direction and B is either into or either out of the paper, always perpendicular to the velocity direction. So what I mean to say is, if it is not perpendicular, there won't be any voltage induced. So let's say our conductor is moving like this, and my magnetic field is like this. So it means it is perpendicularly moving. So then only you will have induced voltage. Now let's say my magnetic lines are like this, and I'm moving my conductor like this, up and down. Then there won't be any induced voltage, because the volt velocity and magnetic field are parallel to each other in this. They are not perpendicular anymore. In that case, there won't be any induced voltage. So if at all they are perpendicular to each other, if at all, then you place that kind of conductor in the magnetic field, which is momentum velocity v of length L, there will be an induced voltage of magnitude BLV, and the polarity of the induced voltage can be found via Fleming's right hand rule. So yeah, this is one of the two rules which is very important in electrical engineering, and we will be using very often down the week's discussion. So I want everyone to remember or understand how we are going to use this Fleming's right hand rule. Excuse me. Yeah. Similarly, now we will look into another rule. We will see what exactly this rule is. Second one. Now, let's say you have this conductor, same conductor we can take of length L, and once again we will place that conductor between North Pole and South Pole. So North Pole is in this side, North Pole is South Pole is bottom. So that magnetic lines of force will be from north to south. In between, I have placed the conductor. But now, to end of this connectors, I am connecting a wire to give a supply. So we will see. Same. This is the conductor X and Y. It is placed in yeah, magnetic field is there again. So it's a cross. Let's say it's cross magnetic field into the paper. Now I have connected these two ends of the wire to a source. Whenever I'm connecting the source, what happens? It will always drive a current through the conductor because it's a current carrying. Conductor can be able to carry a current, so it will drive a current through the conductor. So this is the path of the current source through the conductor, and it will return back to the source. So this is how I'm placing. Now, if you look at the diagram, a conductor is carrying current, and there is magnetic field which is perpendicular to the direction of current flow. Now the current flow is direction is like this, and my magnetic lines of force are into the paper, so they are perpendicular to each other. At this instance, we can always say the conductor will experience some kind of force. That is very important. Whenever a current carrying conductor is placed in a magnetic field, that conductor will experience force. Now, what is the magnet? This conductor length is L. Now, what is the magnitude of this force? Anyone? B I L. This is the magnitude of the force. But what is the polarity of the force? How to find the polarity and which law we will use now? For polarity of the induced voltage, we have used Fleming's right hand rule. For the direction of force experienced by the conductor, we will be using Fleming's left hand rule. That is very important. So force, for the direction of force experienced by the conductor, we will use Fleming's left hand rule. Now, same in our left hand. So this is left hand, and this is the forefinger, and this is the middle finger, and this is the thumb. Again, my forefinger will denote always in both left hand rule and right hand rule. Forefinger always denotes the direction of magnetic field. Okay, this is the magnetic field direction, and my middle finger will denote the direction of current flowing through the conductor, and my thumb will give the direction of the force. I'm writing it here. Forefinger denotes B, middle finger denotes current direction, and my thumb will give the direction of force experienced by the excuse me, conductor. Now if we look at the figure with the left hand rule, my forefinger denotes the direction of the magnetic field, that is into the paper. So this is the direction, and my middle finger should denote the direction of current. It's top to bottom, so this is the direction of my current, and my thumb will give you the direction of force. So my conductor will experience a force which will move the conductor from left to right. So this is the direction of force. This will be the direction of force. Now this will be into the paper, and this will be the down current, and this will be the force direction. Now, yeah. So this is how we will make use of Fleming's left hand rule, and we will try to find the direction of force. Now Fleming's right hand rule, I will just write a simply summary of 1 second. Yeah. Now I will simply write the summary of rules we have seen now. Now right hand rule is for polarity and magnitude of voltages, and left hand rule polarity and magnitude of force. Now, usually it is also said that in electrical engineering, left hand rule is for motors and right hand rule is for generators. It's That's why it's said, because if you see, left hand rule is why it is for motors. Now if you see, you are experiencing some kind of motoring operation in left hand rule. So you are getting some motor, so because of this experienced force, the conductor is moving. So this kind of motoring operation where you are giving supply here. But when you see this right hand rule, you can see some generation of EMF, voltage is being generated here between these two X and Y. Whenever you are placing a conductor which is moving with a velocity v in magnetic field B, EMF will be induced. So that's why it is similar, analogous to generator. Right handed is for generator, left handed is for uh, motors. That's why it's called. It is being said like that. I'm just writing it here. Motoring and generation, so that it will be useful for you down the line when we discuss some numericals on this particular concepts. So yeah, so these are the two laws, very important, that has been discussed with you in this week, as well as I am also discussing again, so that we will be strong enough in this basics of this electrical engineering before proceeding to solve the numericals this week. Now with this information, let's solve the numericals for this week. I will try to discuss some basic concepts on the same concept which we have discussed now. And if you have understood our discussion, these numericals will be very easy for you. So there is no, I hope no one will face difficulty in understanding these questions. And it is very straightforward and very basic questions. Now, let's read the question together, and let's solve the numerical together as well. Now, I request everyone to take pen and paper with them, as well as calculator, and we will try to solve the problems together. So here we are seeing a question. Uh, it's a thought experimental setup. So thought experiment setup means someone wants to set up their experiment like this. So say they imagine it, and they will try to make that experiment. So here we are seeing a north pole at the bottom, south pole on the top. So then the magnetic lines of force will be from north to south. Those are the arrows you are seeing here. Okay, that's fine. And in between, so there is a rail here. There is a rail. On top of it, they placed a conductor AB, and they are pushing it. They are pushing the conductor towards right, from left to right. They are pushing the conductor, and at the end of the railings, they have connected a resistance. So if at all they are providing a closed circuit, so that the current will flow. Okay, that's all. That's fine. Now this is what we are looking at the picture. Now let's read the question. The length of the conductor is given. The length of the conductor AB is of 0.4 meters, and the flux density, magnetic field intensity, is given. B is zero point 0.8 Weber per meter square, or Tesla. Don't confuse. Tesla is also a SI unit, which is equivalent to Weber per meter square. And the resistance we are seeing at the end of the rail is 1 ohm. Okay, everything is fine. Now All other resistances, the conductor resistances, air resistance, rail resistances, everything is negligible. Only resistance present in the circuit is the 1 ohms connected across the terminals of the rail. Now, what else is given? All frictional forces are negligible. There is no friction between the rails and the conductor. Smooth surface, and there is no resistance between the surface and the conductor. Okay, and now the conductor is pushed with a constant force of 100 millinewtons. Now, the value of the force with which we are pushing the conductor is also given. Therefore, at steady state, the conductor will move at a constant speed and a constant EMF will be induced in it, which will drive a constant current through the resistance. Yeah, so that's fine. Now, at the initial instant, we are just pushing the conductor with some force and we are leaving it. Now we will just push it, and after we leave it, since there is no friction between the surface, the conductor will never stop. It will keep on rolling, keep on rolling, keep on rolling, since it's a smooth surface and there is no friction, and it will reach some steady state where the conductor will keep on moving at a constant speed. So in this condition, we saw in the first case, whenever a conductor is placed in kind of magnetic field and force existed, the EMF will be induced in it, which will obviously, whenever there is EMF induced, we are provided a closed path, current will flow. Now, what exactly is asked in this question? We will see. Now, everyone understood the setup. Now, estimate the current that will flow through the resistance in steady state. We are provided with the force, we are provided with the magnetic intensity B, and we know the length of the conductor. How can we find the current? Just now we discussed the formula. Can anyone tell? Very simple formula. The force experienced is equals to BIL. B is given as how much? Zero point 0.8 Tesla, and length of the conductor is zero point 0.4 meter. Force is 100 millinewton. Yeah, 100 millinewton. So what's the current flowing? Current is equals to F by BL. So someone quickly calculate and tell me 100 milli divided by 0.8 into 0.3125 amp. So always once you get the answer, look at the question in what units they are asking. They are asking in the milliamps. So you have to multiply by 10 cube and divide it by 10 cube. So it will give you 312.5 milliamps. Yeah, correct, Raju. So yeah, the direction of force you can find it from the right hand rule. Sorry, left hand rule. Based on the direction of what is the direction of magnetic field intensity, what's the direction of current flowing, and what is the direction of with that you will get the direction of the force. Yeah, and yeah. Now the next question is estimate the induced. Yeah, yeah, sure. Can you estimate the induced EMF now? So again, what is the magnitude of induced EMF we have seen? E is equals to, okay, I will write the formula here. E is equals to BLV, where B is the magnetic field intensity, and L is the length of the conductor, and V is the velocity. But what is the problem with this equation? Now we can't just use any formula we know until unless we have the data here. Now to calculate E, we need B. We have B, we have length, but the velocity is unknown to us. So we can't go with two unknowns. So instead, it's a simple conductor and resistance. We know the voltage induced will be simple Ohm's law IR. Sorry. In the previous question itself, we have calculated the current flowing through the circuit. So we will be making use of that part of the question, and we will find the induced EMF using the current. Now resistance is already known 1 ohm. So 0.3125 multiplied by 1. So the induced voltage will be 0.3125 volts. So there is no need of velocity exactly until unless they ask it now. So since we have the EMF induced now, we can easily calculate back the velocity. Now, in what units they have asked us the voltage? They have asked us the voltage in the, okay, again they have asked us in millivolts. Now the voltage is equals to 312.5 312.5 millivolts. Yeah, it's again a simple problem. Yeah, see, the question is already there. We are expecting this question. So, what is the steady state velocity experienced? What is the velocity with which the conductor will move in its steady state? Now, from the previous question itself, we have calculated the EMF induced, right? Now, yeah, velocity is equals to E by BL. Now, E value is 0.3125 volts divided by how much is B? 0.8 and zero point 0.4. 0.8 multiplied by 0.4. Can anyone tell me how much this is? Sorry, 0.8 into 0.4. Yeah, Karan, it's 0.9765. So it's in meters per second. So yeah, they have asked in centimeters per second again. So to convert, we have to multiply it by 100. 97.65 centimeters per second. So yeah, again, this is always a simple one because when we know the magnitudes, we have just to find what is the unknown and we will calculate it. And the final question which we will see for today is what we have to estimate the power in milliwatts that is required to keep pushing the conductor at the steady state. So yeah, so in order for the conductor to move along the rails, and in order for the conductor to keep remaining in that position and continue its motion in the steady state, what amount of power should be required to supply to that particular conductor? So that's what we have to find. So basic formula for power when we know the force is how to calculate power if we know the force. Can anyone tell? Power is equals to what is the relation between power, force, and velocity? Okay, power is equals to force into velocity. Now, what is the force? It was which is pushed 100 millinewton, right? 100 into 10 power minus 3 newton multiplied by what is the velocity in meters per second? 0.9765. 0.9765. How much is this? Okay. Yeah, again it's 0.97.65 milliwatts. Yeah, that's right, Karan. It's in watts, but it was asked in milliwatts. Anyhow, we have this 10 power minus 3 factor. That's why I'm writing it in milliwatts directly. And another simple way to check it, like if you see, we have just current. We know the current across the uh, current flowing through the conductor and also the resistance. We know power is equals to I square R, right? We can also cross check our answer with it. What is the current we have got? 312.5 milliamps. So 0.3125 square multiplied by 1. So much we got? It's equals to 0.09765 watts. Yeah. So again, it is 97.65 milliwatts. So even this way also you can solve it simple. If you don't exactly recall the relation between force and velocity with the power, and it's always simple to solve I square R formula for the power. So yeah, so this is basically simple numerical problems on the concepts of Fleming's left hand rule and right hand rule. And whenever you are placing a current carrying conductor in a magnetic field, that will experience a force. Whenever you place a conductor in a magnetic field and in magnetic field presence, and the voltage will be induced in it, and how to find the directions of that voltage and how to find the direction of forces. We know I hope you are now clear about what kind of rules we will use. So left hand rule is always used for calculating the direction of forces, and right hand rule is always used for the direction and polarity of the voltages. Left hand is always say that it's for motoring operation, and right hand rule, since it is generating some voltage, we will use it for a generating operations. Now let's quickly go back to the discussion whatever we had today, and just have a summary of whatever we have discussed. So this week we have started with last week's concept of dot convention. Since some of our attendees are having a confusion in dot convention, so those who have joined late, they can refer to the recording that will be present on the YouTube after this class. I will upload it. So please go through basics of this dot convention which I discussed. So in this we have started from very basic. What is a coupled circuit? And what kind of coupled circuits are present, electrical coupling and magnetic coupling, and within a electric coupling magnetic coupling, what exactly dot convention means, and how we will determine the polarity of the voltage using the dot convention. And within that we have seen aiding and opposing type in both electric coupling and magnetic coupling as well. In electric coupling we will see there are series connected coils, and we found that the total equivalent inductance is aiding in case of if the current is entering at the two dots, both dots of current is entering, and we have seen that the equivalent inductance reduces the self inductance, and mutual inductance will be opposing each other when the dots are at one dot current is entering and at another dot the current is leaving. This is in case of electrical coupling; those are connected in series. And yeah, we saw the same kind of discussion in magnetic coupling as well, where in the magnetic coupling we saw the aiding type and opposing type as well. And within that, there is no any physical connection. Entire mutual coupling we have saw due to the currents responsible flowing through the two different coils. Here the currents are different because there is no series connection, and I1 and I2 responsible for the mutual inductance for the second coil and primary coil respectively. And within this coupling connection, magnetic coupling connection, we have seen aiding type and opposing type. So aiding means both self-inductance and mutual inductance will have the same polarity. In opposing type, self-inductance and mutual inductance will have the opposite polarity. And with that, we close the discussion for the coupling circuits, and we have started today's discussion with two very important and basic electrical engineering laws, that is Fleming's right hand rule and Fleming's left hand rule. And we have discussed a case where we are placing the conductor in a magnetic field and it is moving with a velocity v of length L. Now then the EMF will be induced in that conductor across the inductor, and what is the magnitude and what is the polarity. We have found that using the Fleming's right hand rule, and we can always reverse the polarity of the induced EMF by just reversing the direction of magnetic field. If you replace north and south pole, north bottom and south bottom, the magnetic field will be reversed. Corresponding induced EMF polarity will also be reversed. That's what we have just mentioned in this case. So here it is plus minus, it is minus plus, just because of here it is cross and here it is dot. So that's an important point. How will you reverse the polarity? By reversing the magnetic field. Even later when we discuss the machines, AC machines as well, AC machines will rotate in this direction. If we want to reverse it, we will just replace the connection, or else we can also reverse the magnetic field generated. So yeah, and then we move to Fleming's left hand rule. In this case, we are placing a current carrying conductor in a magnetic field. How the current is carrying in the conductor, we are giving an external source to it, so that's there. Now whenever we are providing a source and the current, we made the current to pass through the conductor, and then the current carrying conductor placed in the magnetic field will experience a force. So how to find the direction of force? We will be using the Fleming's left hand rule. So the direction of thumb will give the direction of force. So using that, we will determine the direction. And yeah, that's a summary. Using right hand rule and left hand rule, we find the polarities of voltages and force respectively. And with that, we have discussed a simple thought experimental setup, uh, where we are given with all the data and we are asked to find individually what is the current flowing through the resistance in the steady state, what is the induced EMF under steady state, and what is the velocity under steady state, and what is the power required to keep pushing the conductor to steady state. So yeah, so I hope everyone understood today's discussion, and we have gone very slow. We have covered every topic very slowly, so that I won't rush things with you. And for the last week also, we have discussed the dot convention in detail this week. So I hope it is clear for you now. And if you have any doubts in today's discussion, you can always ask, unmute yourself and ask. And okay. Uh, Every week we are lagging by one assignment. Assignment we have solved today, for that assignment submission is already over and tomorrow is the last date for third assignment. So please explain numericals for third assignment that will help us. I doubt it. Okay, you have already solved. Okay, we are lagging by 1 week. Okay, okay, I understood. Next week, okay, next week, Wednesday, you will be submitting fourth assignment, week 4. Okay, for third assignment, 15th is the last date. Okay, 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 I understand. So, I didn't know this. So, and for fourth assignment, 22nd Feb, right? So, our next session will be on 21st. Okay, then let's discuss week 4 from 22nd February. So, I understood. I got the point, and I hope, yeah, okay. I'm sorry for the confusion. So, because this is our second week, but how come it's third assignment already? Maybe, okay. I will check the dates once again, because your courses are started from Feb 3rd and your first assignment should be submitted by 8th. I have taken 7th. When did you submit your first assignment? When was the last? So on 15th you are submitting first and second. Okay, for the second assignment also 8th was the due date. So okay, got it. Okay. Sorry for the confusion. I didn't know that first and second assignments were completed by 8th. Or else in the last week itself, I have covered these concepts. Okay. Let's do this thing. From next week, I will discuss the fourth week concepts. Then we will be in sync from next week. Thanks for informing me. And from next week, we will see week 4 concepts. Yeah, with that, thank you for informing and thank you for joining the session and listening to me patiently and cooperating with me. And yeah, with that, if there are no more doubts for you in this week, and If there are no more queries to discuss or some points to discuss, we will take leave for this session. And please do raise questions in discussion forum also if you are having some kind of doubts. And please feel free to ask any kind of question there, and we will be always available. Uh, so, okay, number of third assignments today. Okay, I will ask the. Okay, I also have some kind of commitment now. I have another meeting now. Right now, I cannot solve. One thing I will do, I will ask one more TA is there. I will ask him to arrange a session today or tomorrow so that they will solve the third. He will solve the third assignment questions with you. I will talk to the one more TA. Okay, I understand. Okay, yeah, sure. I understood that. I will talk to the other TA and I will communicate with him as well. So to solve some third assignment questions. You will get this live video by this evening. Yeah. Are you not being shared with the live video links of this in the YouTube? Because there is a sheet where we are uploading our live video links. Channel name is my name only. Ambulance. I let me drop the question. Let me drop the channel link here. So, okay, not Soya map. Maybe you have to. Okay, I have dropped the channel link there. That's my channel where we have to upload all our videos. And today's video you will always get by the end of the same day. So I won't lag that much. As soon as I complete the session, I will upload the video there. Sorry, every section means what is the section? Previous. So in the I didn't understand. In that channel if you go, you will have last week's video and this week's video and next week's also. I will upload in this channel only. So in this link you will find in this link you will find the last week's video as well. Okay. Okay, thank you once again and thanks for joining, and see you next week with the week 4 content. Thank you.